Okay, I want to show you how to tackle graphing a cosecant curve. And really what we're going to do is focus on the fact that cosecant is simply the reciprocal of the sine function. And so if we can graph a sine and we know a little bit about how rational functions work, we can move from there. So first thing I want to do is realize that typically in these problems, they don't do a whole lot with horizontal shifts and vertical shifts. Most textbooks are set up and they really focus on a value that's going to provide some sort of vertical stretch, that 4 out in front, and then a value that's going to affect the period of the function, this 2 pi over 3 there that's being multiplied by your variable. So make a little list here. The a value is 4 and the b value is 2 pi over 3. And sort of what we're thinking is kind of, could we graph 4 sine 2 pi over 3x? And if we can graph that, being the reciprocal of the cosecant function, we should be good to go to graph the cosecant function. So first thing I'd recognize is that b is 2 pi over 3, and we know for sine and cosine the period is 2 pi over b. So if we set up our period to be 2 pi over b, but that's 2 pi over 2 pi over 3, and simplify that to 2 pi times 3 over 2 pi, we get a period of 3. So 1/4 of our period is 1/4 of 3, or 3/4. I always like to figure out what a quarter of the period is going to be. So if we were going to graph this thing, I'd want to have my period established to be 3. So I'm going to go over here to the right side of my graph and put a 3 there. And then I come about halfway along here and split that distance in half by dividing by 2. I will split that distance in half by dividing by 2 again, making it 3/4. And then this third spot right here is always 3 of these things. So 1/4, 2/4, 3/4, and 4/4 of the period. So right in that spot there, I want to have 3 times 3/4, which is 9/4. So again, I just took this value and multiplied it by 3 for that value. So now I have a graph that's set up to deal with this period of 2 pi over 3. I want to set my vertical scale of my function by recognizing that this graph, if I was looking at 4 sine of 2 pi over 3x, it would go up to 4 and it would go down to a minimum of -4. And if you know your sine curve well, you would know that the sine curve starts at the origin and then it moves up by the time you're at a quarter of a period. So it would kind of come up like this and then max out at a quarter of the period. It's going to hit the x-axis back at half the period before it goes down and goes to its negative min at -4 at 9 pi over 4 and then back to 0. So a sine curve, this sine curve would look like that, and we'd be all set. The thing is here, if we think of cosecant, the cosecant of x being 1 over the sine of x, whenever you have a rational function, you want to focus on the denominator being 0. In other words, what does it take to make the denominator 0? Well, the sine, in this case, we have the sine of 2 pi over 3x. So we can see exactly where that's going to be 0. It's going to be 0 right here, right here, right here. And so when that quantity winds up being in the denominator, if we have 1 over that, our function that we're graphing, this cosecant, is going to have a vertical asymptote at those values, because that's what happens to a graph when you divide by 0. When you have a quantity or an x value that makes the denominator 0, that's when you're going to get a vertical asymptote showing up. So just kind of understanding how those rational functions work when you get vertical asymptotes, I can just draw in some vertical asymptotes right there and right there. So our graph, cosecant graphs, as well as secants, will have vertical asymptotes at any place. Cosecants will have any place vertical asymptote wherever the sine is 0. So I would put a little equation of that vertical line: x equals 0, x equals 3/2, and x equals 3. Most teachers, most textbooks will look for you to be able to draw those vertical asymptotes and show their equations, always a vertical line, so it's going to be x equals. And now the second part of this task is really pretty simple, because if you think about when when you've got an a value of 4, as we do in this case, 4 times the cosecant of 2 pi over 3x, what that is 4 times 1 over the sine of 2 pi over 3x. So the largest this value can ever be the largest that this value can ever be is 1. So when we divide by sine of 2 pi over 3x instead of multiplying by sine of 2 pi over 3x, we want to realize that if this value down here in the denominator turns out to be 1, we're going to get a y value of 4. So kind of like thinking 1 is the number that is its own reciprocal. So what's going to happen is our cosecant curve is just going to have this value of 4 here when the sine of 2 pi over 3 is equal to 1. So we can take our curve and realize that our cosecant curve is just going to kiss the sine curve right there at its maxes and its mins. And so what you're seeing here in the thick completed blue curve is the graph of one period of the cosecant of 2 pi over 3x with a 4 out in front. And that's generally what teachers and textbooks are looking for, is maybe one period or maybe 2 periods. But essentially, the mission is draw the sine curve that's associated with it, and wherever the sine curve has an x-intercept, draw in a vertical asymptote, and wherever the sine curve has a max or a min, that becomes the opposite of that in the cosecant curve. So in other words, the max of the sine curve at 3/4 is going to be the min of the cosecant curve. The max down here, the minimum value of this sine curve is going to be the max of that cosecant portion. So there you go. Okay, for this example, we're looking at a secant curve. And of course, secant is the reciprocal of cosine. So as long as you were okay with the cosecant curve being the reciprocal of sine, we're going to approach this one in the same way. So in other words, we're going to think about what would its associated cosine curve be. And that would be y equals -1/2 cosine of 3x over 4. So again, my a value is -1/2 and my b value is 3/4. The period is 2 pi over b, which in this case is 2 pi over 3/4, which is 2 pi times 4/3, which is 8 pi over 3. So I'm going to come out here to the end of my curve and put in 8 pi over 3. Realize that 1/4 of my period would be 1/4 of 8 pi over 3, which is just 2 pi over 3. So that's to be expected. When I take half of my period, that would be 4 pi over 3. 1/4 of the period is 2 pi over 3. And then, again, same technique as last time. This is 1/4, 2/4, 3/4. So 3/4 of my period is going to be 3 times this. Well, 3 times 2 pi over 3 is just going to be 6 pi over 3, which is 2 pi. So I've got my x-axis scaled, and again, I look to my a value for my cosine is -1/2. So disregarding that negative sign for just a second, the a value or the amplitude rather, of being 1/2, I could put that there and put that there. Now, I wanted to do one of these so that it had a negative a value so you could recognize how you deal with a negative, which of course, multiplying a function by a negative results in a reflection of the graph over the x-axis. So we want to think about a cosine curve that's going to follow 1/2 cosine of 3x over 4, and then just think about it being reflected over the x-axis. So normally a cosine curve starts at its maximum value, which in this case would be 1/2, but because of the negative sign, it's going to start at its minimum value of -1/2. Forgot my negative sign there. So let's, that guy right there. Let's start our cosine curve so that it's down here at its negative. 1/4 of the way through the period, it's going to be at 0. Then it's going to be up at its max. And then it's going to be back down to 0. And then it's going to have its min. So just like we did last time, because secant is the reciprocal of cosine. Whenever cosine has an x-intercept like it does here, we're going to see a vertical asymptote. And whenever it has a maximum or a minimum, that's where the secant curve is going to touch base. So if I can just draw the associated secant curve now, starting here at this point where the secant or the cosine has its minimum, it's going to be the maximum for the secant curve. Up here, when it has its cosine has its max, secant will have its minimum. And then when cosine has its minimum, it'll be down there again. And if you want to be fancy about it, you come back and erase these dotted lines that were associated with our cosine curve to make it look like you did it without even thinking about the cosine. But there you go. That would be one period of a secant curve.